LaND, learning to navigate from disengagements. Testing is a crucial part of developing autonomous mobile robot systems. Here, we see a sidewalk delivery robot being tested. A person is monitoring the robot and disengages and repositions the robot each time it fails. Typically, these failures are then used to help the autonomy developers debug the software. However, this debugging process is highly non-trivial, system-dependent, and laborious, especially for learning-based components. In contrast, our approach uses these disengagements as a direct learning signal for navigation. We call our method learning to navigate from disengagements, or LaND. Our method works by learning from data that is already collected during standard testing. For our sidewalk robot, this includes disengagements resulting from driving into a driveway, colliding, and driving into the street. The dataset consists of only the robot's onboard sensors, such as camera images, the robot's commanded actions, such as the steering angle, and whether the robot autonomy mode was engaged or disengaged. We then learn a predictive model that takes as input the current sensor observations and a sequence of future planned actions, and predicts whether the robot will be engaged or disengaged in the future. Here, we visualize the neural network's predictions for which actions lead to disengagements. Using this neural network, the robot can then plan and execute actions that avoid disengagements. We evaluated our approach using a sidewalk delivery robot and collected 17 kilometers worth of data containing 2,000 disengagements. We compared our approach with two methods: behavioral cloning, an imitation learning approach used by many state-of-the-art navigation methods, and a reinforcement learning algorithm, which first learns a compressed image representation using a VAE, and then uses this representation with the DDPG reinforcement learning algorithm. We evaluated all approaches over 2.3 kilometers of sidewalks, not seen in the training set. Our approach was able to travel the furthest before disengagement, traveling over 6 times further than the behavioral cloning policy. Here, we show examples of our approach successfully navigating near a parked bicycle, a sharp turn, near dense foliage, and in sun glare, while the behavioral cloning policy fails. Now we show our approach navigating the full 2.3 kilometers of sidewalks. We also investigated the ability of our method to continuously improve as more data is gathered. In this controlled experiment, we first ran our method on 1.3 kilometers of sidewalk. We then trained our method on this additional data and evaluated this fine-tuned model on the same 1.3 kilometers of sidewalk. Our method improves by over 2 times when fine-tuned on the collected data, showing that our approach is able to continue to improve as more data is collected. Thank you for watching.